As we discussed in Chapter 8, bonds can be polar. When there's large differences in electronegativity between two elements, we create a distortion in the covalent bond with the electrons favoring one side versus the other. Well, in molecules, polarity can manifest itself in a number of different ways. You can have polar molecules because you have polar bonds, but you can also have a nonpolar molecule when there are polar bonds. It's the sum of the pull on the central atom that dictates whether or not a molecule is polar. Think about polarity of a molecule in terms of a tug-of-war. In carbon dioxide's case here, we can see we have a carbon-oxygen bond, and those two bonds create a dipole moment. However, because they are oriented 180 degrees from each other, they're both pulling equally on that carbon, effectively canceling each other out. So while carbon-oxygen has a polar bond, carbon dioxide is a nonpolar molecule because the net pull on that central atom is zero. So we have to look at the individual tug-of-war on the central atom. If everything isn't balanced out, then we're going to have a polar molecule, and most molecules are polar. As we see in this slide here, we have a number of different polar and nonpolar molecules. If we look at HCl, for example, we see that hydrogen chloride as a gas has a dipole moment, making it a polar molecule. It's linear, and there's nothing to offset that pull from the chlorine on the hydrogen. We see over here with NH3, we have a polar molecule. Nitrogen's blue, the three white spheres, those are hydrogens. And while they're pulling equally on the nitrogen, there's a lone pair of electrons above the three here, which is not pulling at all. So there is a net dipole moment in this molecule, making it polar. On the other hand, if we look at CCl4 here, carbon tetrachloride, we can see carbon is surrounded by four identical atoms in this tetrahedral shape. There are four domains, all of them occupied by chlorine. So while a carbon-chlorine bond is polar, the net effect is this tug-of-war. No one wins. It cancels out. Likewise, boron trifluoride has a very similar circumstance. We have a trigonal planar structure. We have a boron-fluorine bond, which is polar. However, because the bond angles are 120 degrees, they're all pulling equally on the boron. They cancel each other out, leaving a nonpolar molecule.